In the name of Almighty God, I'm Mahsa Sankosha, and today I want to talk about gear shifting in a sequential gearbox. On a sequential gearbox, you simply push the lever up for a very gear change. The sequential shift is consistent and you don't have to think, let's see, I'm in second gear, so I have to go up over up to get to third. You simply push the lever forward. It's the same motion for every gear. This example illustrates the modeling of a sequential manual transmission where the gears are selected sequentially with the help of a rotating drum. The shift drum has two grooves of a specific profile carved around the circumference. As the drum rotates, the grooves on the drum guide a set of shift forks, which is turn, helps in engaging the required gear. A transient multibody analysis is performed to simulate the gear shifting mechanism and compute the angular velocity of all the gears for the specified engine speed. And what about sequential manual transmission? A sequential manual transmission, also known as a sequential gearbox for sequential transmission, is a type of non-synchronous manual transmission used mostly in motorcycles and racing cars. It produces faster shift times than traditional synchronized manual transmissions and restricts the driver to selecting either the next or previous gear in a successive order. And what about the design? A sequential manual transmission is unsynchronized and allows the driver to select either the next gear, for example, shifting from the first gear to second gear, or the previous gear, for example, shifting from the third gear to second gear. Operated either via electronic paddle shifters mounted behind the steering wheel or with a sequential shifter. This restriction avoids accidentally selecting the wrong gear. However, it also prevents the driver from deliberately skipping gears. The use of the dog clutches rather than synchronomesh results in faster shift speeds than a conventional manual transmission. On a sequential manual transmission, the shift lever operates a ratchet mechanism that converts the force and aft motion of the shift lever into rotation of a gear shift drum or selector drum, sometimes called a barrel, which has three or four tracks machined around its circumference. Selector forks are guided by the tracks either directly or via selector rods. The tracks deviate around the circumference, and as the drum rotates, the selector forks are moved to select the required gear. When upshifting or downshifting a sequential manual transmission, there is no need to operate the clutch, which is only required when the vehicle starts. Since the engagement ring or dog ring is pushed by the shift fork and moves quick, and the engagement ring begins to transmit power synchronously while it comes into contact, the sequential manual transmission has the shortest shift speed, and the shift time is usually 5 milliseconds or less and is therefore now used in all Formula One cars. A sequential manual transmission is not to be confused with the pneumatic sequential shifting function, sometimes fitted to hydraulic automatic transmission marketed with trims such as Tiptronic or a sport shift. This function allows the driver to select the previous or next gear through the use of the buttons or a lever usually near the gear shifter or a steering wheel. However, the mechanics of transmission are unrelated to a true sequential manual transmission. And what about the usage? Most motorcycles use a sequential manual transmission. The rider controls the gear shifter with their foot, allowing their hands to remain on the handlebars. And gear selection uses a layout of 1 and 2, 3, 4, 5, or 6. For a typical 6 speed gearbox set as 1 down, 5 up. However, most modern motor scooters don't use a sequential manual transmission, instead using either a hydraulic automatic transmission or a belt-driven or chain-driven continuously variable transmission under bonds. However, often use a semi-automatic transmission with an automatic centrifugal clutch, but will still retain the conventional foot-operated gear shift lever, such as the Honda Super Coupe. And what about the history? The first proper sequential manual gearbox used in a race car was with Porsche Type 360 in 1946, followed by the infamously unreliable gearbox design pioneered by Richard and Stahle and Harry Mandy, which was used in various Lotus Grand Prix race cars during the late 1950 and early 1960, beginning with the 1958 Lotus 12, and is technically the first proper sequential gearbox used in a race car. Most racing cars also use a sequential transmission now, via a sequential shift lever with a mechanical linkage or electronic paddle shifters, rather than the old H-pattern stick shift, beginning with the paddle-shifted Ferrari 640 Formula One car in 1990, which used a sequential drum rotation mechanism. The first modern sequential manual gearbox with a manual shift lever was used in the 1990 Peugeot 905 Group C sports car, followed by the Ferrari 330 SPLMP race car and kart champ karts in 1994 and 1996, and then the McLaren F1 GTR and Mercedes-Benz CLK GTR, Porsche 911 GT1 and Panoz Sprante GTR1 GT1 race cars in 1996 and 1997. This was closely followed by the WRC rally cars in 1997 and 1998 and 1999, and also the Porsche LMP 196, Nissan R390 GT1 and Toyota GT1, and the BMW V12LM and LMR Le Mans prototype race cars in 1998 and 1999. Touring cars have also used sequential manual gearbox, starting with the European DTM series in 2000, which used it for 12 seasons until a switch to a paddle shift system in 2012. The Australian V8 Supercars series started using sequential manual gearbox in 2008 after switching from an H-pattern manual gearbox, and NASCAR introduced a 5-speed sequential manual transmission with their Gen 7 car in 2022 after using conventional 4-speed H-pattern manual transmission for many years. Due to the high rate of wear and abrupt shifting action, sequential manual transmissions are rarely used in passenger cars, albeit with some exceptions. And what about the manual transmissions? Manual transmissions, or MT, also known as manual gearbox standard transmission in Canada and UK, US, or stick shift in the US in a multi-speed motor vehicle transmission system where gear changes require the driver to manually select the gears by operating a gear stick and clutch, which is usually a foot pedal for cars or a hand lever for motorcycles. Early automobiles used sliding mesh manual transmissions with up to 3 forward gear ratios. Since the 1950, constant mesh manual transmissions have become increasingly commonplace, and the number of forward ratios has increased to 5-speed and 6-speed manual transmissions for current vehicles. The alternative to a manual transmission is an automatic transmission. Common types of automatic transmissions are the hydraulic automatic transmission or AT and the continuous variable transmission or CVT. The automated manual transmission or AMT and the dual clutch transmission DCT are internally similar to a conventional manual transmission but are shifted automatically. Alternatively, there are semi-automatic transmissions. These systems are based on the design of and are technically similar to a conventional manual transmission. They have a gear shifter which requires the driver's input to manually change gears, but the driver is not required to engage a clutch pedal before changing gear. Instead, the mechanical linkage for the clutch pedal is replaced by an actuator, servo, or solenoid and sensors, which operate the clutch system automatically when the driver touches or moves the gear shift. This removes the need for a physical clutch pedal. A manual transmission requires the driver to operate the gear stick and clutch in order to change gear, unlike an automatic transmission or semi-automatic transmission, where one, typically the clutch or both of these functions, are automated. Most manual transmissions for cars allow the driver to select any gear ratio at any time, for example, shifting from the second to fourth gear or fifth to third gear. However, sequential manual transmissions, which are commonly used in motorcycles and racing cars, only allow the driver to select the next higher or next lower gear. In a vehicle with a manual transmission, the flywheel is attached to the engine's crankshaft, therefore rotating and at engine speed. A clutch disc sits between the flywheel and the transmission pressure plate, which is attached to the transmission input shaft, controlling whether the transmission is connected to the engine or not. The clutch pedal controls the pressure plate. Clutch engage. The clutch pedal is not being pressed or not connected to the engine. Clutch in this engage. The pedal is being pressed down. When the engine is running and the clutch is engaged, for example, clutch pedal up, the flywheel spin the clutch pressure plate and hence the transmission. The design of most manual transmissions for cars is that gear ratios are selected by locking selected gear pairs to the output shaft inside the transmission. This is a fundamental difference compared with the typical hydraulic automatic transmission, which uses an epicycle planetary design and a hydraulic torque converter. An automatic transmission that allows the driver to control the gear selection, such as shift pedals or positive negative positions on the gear selector, is called a pneumatic transmission and is not considered a manual transmission. Some automatic transmissions are based on the mechanical build and internal design of a manual transmission but have added components such as computer control actuators and sensors, which automatically control the timing and speed of the gear shifts and clutch. This design is typically called an automated manual transmission or sometimes a clutchless manual transmission. Contemporary manual transmissions for cars typically use 5 or 6 forward gears ratio and 1 reverse gear. However, transmissions with between 2 and 7 gears have been produced at times. Transmissions for trucks and other heavy equipment often have between 8 and 25 gears. In order to keep the engine speed within the optimal power band for all typical road speeds, operating such transmissions often uses the same pattern of shifter movement with a single or multiple switches to engage the next sequence of gears. And what about the history between 18th 19th century to 1940? Many of the first automobiles were rear-engined with a simple belt drive functioning as a single-speed transmission. The 1891 Panhard and its Lavalier is considered a significant advance in automotive transmission since it used a three-speed manual transmission. This transmission, along with many similar designs that it inspired, was a non-synchronous, also called sliding mesh design where gear chains involved sliding the gears along their shafts so that the desired cogs became meshed. The driver was therefore required to use careful timing and throttle manipulation when shifting. So the gears would be spinning at roughly at the same speed when engaged. Otherwise, the teeth would refuse to mesh. This was difficult to achieve, so gear changes were often accompanied by grinding or crunching sounds, resulting in the gearbox being nicknamed crash box. Even after passengers' car had switched to synchronized transmissions, for example with synchronizer, many transmissions for heavy trucks, motorcycles, and racing cars remained non-synchronous in order to withstand the forces required or provide a faster shift time. The first car to use a manual transmission with synchronous mesh was the 1929 Cadillac. Most North US marques had adopted synchronized manual transmissions, usually for second and higher gears. By the mid-1930s, in 1947, Porsche patented the split ring synchronomesh system. The 1952 Porsche 356 was the first car to use a transmission with synchronomesh on all forward gears. In the early 1950s, most cars are only had synchronomesh for the shift from the third gear to second gear. Drivers' manuals in vehicles suggested that if the driver needed to shift from the second to first, it was best to come to a complete stop beforehand. Up until the late 1970s, most transmissions had three or four forward gear ratios. Although five-speed manual transmissions were occasionally used in a sports car, such as the 1980 48 Ferrari 166 Inter and the 1953 Alfa Romeo 1900 Super Sprint. Five-speed transmissions became widespread during the 1980s, as did the use of synchronomesh on all forward gears. And what about the 1990 to present? Six-speed manual transmissions started to emerge in high-performance vehicles in the early 1990s, such as the 1990 BMW 850i and the 1992 Ferrari 456. The first six-speed manual transmission was introduced in the 1967 Alfa Romeo 33 Stradale. The first seven-speed manual transmission was introduced in the 2012 Porsche 911. In 2008, 75.2% of vehicles produced in Western Europe were equipped with manual transmission versus 16.1% with automatic and 8.7% with others. And what about the internal shafts? A manual transmission has several shafts with various gears and other components attached to them. Most modern passenger cars use constant mesh transmissions consisting of these shafts and an input shaft, a counter shaft also called lay shaft, and an output shaft. The input shaft is connected to the engine and spins at engine speed whenever the clutch is engaged. The counter shaft has gears of various sizes which are permanently meshed with the corresponding gear on the input shaft. The gears on the output shaft are also permanently meshed with a corresponding gear on the counter shaft. However, the output shaft gears are able to rotate independently of the output shaft itself through the use of bearings located between the gears and the shaft. Through the use of collars operated using the shift rods, the speed of the output shaft becomes temporarily locked to the speed of the selected gear. Some transmission designs, such as in Volvo 850 and S70, have two counter shafts, both driving and output pinion meshing with a front-wheel drive transaxle ring gear. This allows for a narrower transmission since the length of each countershaft is half compared with one that contains four gears and two shifters. The fixed and the free gears can be mounted on either the input or output shaft or both. For example, a 5-speed transmission might have the first to second selectors on the countershaft, but the third to fourth selector and the fifth selector on the main shaft. This means that when the vehicle is stopped and idling in neutral with the clutch engaged and the input shaft spinning, the third, fourth, and fifth gear pairs don't rotate. When neutral is selected, none of the gears on the output shaft are locked to the shaft, allowing the input and output shafts to rotate independently. For reverse gear, an idler gear is used to reverse the direction in which the output shaft rotates. In many transmissions, the input and output shafts can be directly looped together bypassing the countershaft to create a one-to-one gear ratio, which is referred to as direct drive. In a transmission for longitudinal engined vehicles, for example, most rear-wheel drive cars, it is common for the input shaft and output shaft to be located on the same axis, since this reduces the torsional forces to which the transmission casing must withstand. The assembly consisting of both the input and output shafts is referred to as the main shaft. Also, sometimes this term refers to just the input shaft or output shaft. Independent rotation of the input and output shafts is made possibly by one shaft being located inside the hollow bore of the other shaft, with a bearing located between the two shafts. In a transmission for transverse engine vehicles, for example front-wheel drive cars, there are usually only two shafts, input and counter shaft, sometimes called input and output. The input shaft runs the whole length of the gearbox and there is no separate input pinion. These transmissions also have an integral differential unit which is connected via a pinion gear at the end of the counter output shaft. And what about the dog clutch? In a modern constant mesh manual transmission, the gear teeth are permanently in contact with each other and dog clutch, sometimes called dog teeth, are used to select the gear ratio for the transmission. When the dog clutch for all gears are disengaged, for example, when the transmission is in neutral, all of the gears are able to spin freely around the output shaft. When the driver selects a gear, the dog clutch for that gear is engaged via the gear selector rods, locking the transmission's output shaft to a particular gear set. This means that the output shaft rotates at the same speed as the selected gear, thus determining the gear ratio of the transmission. The dog clutch is a sliding selector mechanism that sits around the output shaft. It has teeth to fit into the splines on the shaft, forcing that shaft to rotate at the same speed as the gear hub. However, the clutch can move back and forth on the shaft to either engage or disengage the splines. This movement is controlled by a selector fork that is linked to the gear lever. The fork doesn't rotate, so it is attached to a collar ring on the selector. The selector is typically symmetric. It slides between two gears and has a synchronomesh and teeth on each side in order to lock either gear to shaft. Unlike some other types of clutch, such as the foot-operated clutch of a manual transmission car, a dog clutch provides a non-slipping coupling and is not suited to intentional slipping. And what about the synchrono mesh? In order to provide a smooth gear shifts without requiring the driver to manually match the engine revs for each gear shaft, most modern passenger car transmissions use synchrono mesh, also called synchronizer rings on the forward gears. These devices automatically match the speed of the input shaft with that of the gear being selected, thus removing the need for the driver to use techniques such as double clutching. The synchronomesh transmission was invented in 1990 by Earl Avery Thompson and first used on production cars by Cadillac in 1928. The need for synchronomesh in a constant mesh transmission is that the dog clutch requires the input shaft speed to match that of the gear being selected. Otherwise, the dog teeth will fail to engage and a loud grinding sound will be heard as they clatter together. Therefore, to speed up or slow down the input shaft as required, cone-shaped brass synchronizer rings are attached to each gear. When the driver moves the gearshaft lever towards the next gear, these synchronizer rings press on the cone-shaped sleeve on the dog collar so that the friction forces can reduce the difference in rotational speeds. Once these speeds are equalized, the dog clutch can engage and thus the new gear is now in use. In a modern gearbox, the action of all of these components is smooth and fast. It is hardly noticed. Many transmissions don't include synchronomesh on the reverse gear. See reverse gear section below. The synchronomesh system must also prevent the collar from bridging the locking rings while the speeds are still being synchronized. This is achieved through blocker rings, also called bulk rings. The synchro ring rotates slightly because of the frictional torque from the cone clutch. In this position, the dog clutch is prevented from engaging. Once the speeds are synchronized, friction on the blocker ring is revealed and the blocker ring twists slightly, bringing into alignment certain grooves or notches that allow the dog clutch to fall into the engagement. Common metals for synchronizer rings are brass and steel and are produced either by forging or sheet metal shaping. The latter involves stamping the piece out of a sheet metal strip and then matching to obtain the exact shape required. The rings are sometimes coated with anti-wear linings, are also called friction linings, made from molybdenum, iron, bronze, or carbon, with the latter usually reversed for high performance transmission due to their high cost. Mechanical wear of the synchronizer rings and sleeves can cause the synchronomesh system to become ineffective over time. These rings and sleeves have to overcome the momentum of the entire input shaft and clutch disc during each gear shaft and also the momentum and power of the engine. If the driver attempts a gear shift without fully disengaging the clutch, larger differences in speed between the input shaft and the gear require higher friction forces from the synchronomesh components, potentially increasing their wear rates. Reverse gear. Even in a modern transmission where all of the forward gears are in constant mesh configuration, often the reverse gear uses the older sliding mesh or crash bus configuration. This means that moving the gear shaft lever into reverse results in gears moving to mesh together. Another unique aspect of the reverse gear is that it consists of two gears, an idler gear on counter shaft and another gear on the output shaft, and both of these are directly fixed to the shaft. For example, they are always rotating at the same speed as the shaft. These gears are usually spare gears with straight cut teeth, which, unlike the helical teeth used for forward gear, results in a whining sound as the vehicle moves in reverse. When reverse gear is selected, the idler gear is physically moved to mesh with the corresponding gears on the input and output shafts to avoid grinding as the gears begin to the mesh. They need to be stationary since the input shaft is often still spinning due to momentum. Even after the car has stopped, a mechanism is needed to stop the input shaft, such as using the synchronizer ring for fifth gear. However, some vehicles do employ a synchronomesh system for the reverse gear, thus preventing possible crunching if reverse gear is selected while the input shaft is still spinning. Most transmissions include a lockout mechanism to prevent reverse gear from being accidentally selected while the car is moving forward. This can take the form of a collar underneath the gear knob, which needs to be lifted or requiring extra force to push the gear shaft lever into the plane of reverse gear. And what about the non-synchronous transmission? Another design of transmission that is used in older cars, trucks, and tractors is a non-synchronous transmission, also known as a gearbox. Non-synchronous transmissions use a sliding mesh or constant mesh in later years. Design and have the nickname crash because the difficulty in changing gears can lead to gear shifts accompanied by crashing, crunching noises. Vehicles with manual transmissions use a clutch to manage the linkage between the engine and the transmission and decouple the transmission from the engine during gear shifts. And when the vehicle is stationary without a clutch, the engine would stall anytime the vehicle stopped. The changing gears would be difficult. Deselecting a gear while the transmission requires the driver to adjust the throttle so that the transmission is not under load, and selecting a gear requires the engine RPM to be at the exact speed that matches the road speed for the gear being selected. Most motor vehicles uses a pedal to operate the clutch, except for motorcycles, which usually have a clutch lever on the left handlebar. In most vehicles with a manual transmission, a driver selects gears by manipulating a lever called a gear stick, also called as a gear shift or gear lever or shifter. In most automobiles, the gear stick is located on the floor between the driver and the front passenger. But some cars have a gear stick that is mounted to the steering column or the center console. The movement of the gear stick is transferred via the solid linkage of or cables, so to the selector forks within the transmission. Motorcycle typically employ sequential manual transmissions, although the shift pattern is modified slightly for safety reasons. Gear selection is usually via the left foot or on the older motorcycle right foot. Shift lever with a layout of 1 and 2, 3, 4, 5, 6. 3 on the tree versus 4 on the floor. During the period when used vehicles usually had only three forward speeds, the most common gear shift location was on the steering column, a layout that was sometimes called the tree and the tier by contrasting high-performance cars and European vehicles in general. mostly used a four-speed transmission with floor-mounted shifters. That layout was referred to as four on the floor. Most FR front engine rear-wheel drive vehicles have a transmission that sits between the driver and the front passenger seat. Floor-mounted shifters are often connected directly to the transmission, and fronted engine or front wheel drive vehicles are rear engine or rear wheel drive vehicles, and front engine vehicles with rear mounted gearbox often require a mechanical linkage to connect the shifter to transmission. Column mounted shifter clutch. Some vehicles have a gear lever mounted on the steering column. A three-speed column shifter, which came to be popularly known as a tree on the tree, began appearing in America in the late 1930s and became common during the 1940s and 1950s. If a used vehicle was equipped with override, it was very likely to be a board warner type operated by briefly backing of the accelerator pedal when above 28 mph or mile per hour, which is equal to 45 km per hour to enable, and momentarily flooring the same pedal to return to normal gear. The control simply disables override for such situations as parking on a hill or preventing unwanted shifting into override. And here you can see that I have used the multibody dynamic as a physical module and the structural steel for the material of this gearbox. And for the example, for parameters, you can see the number of teeth is about 20 teeth. It's for first gear, second gear, third gear, and just for second gear there is 44 teeth, and number of teeth for third gear output shaft is 28, and 20 again for number of teeth for fourth gear. And the other parameters is gear ratio first gear, uh, gear ratio for second gear, and for until fourth gear, and center distance between shafts, and the pitch diameter for all of the gear, for example first to fourth gear, and pressure angle is 25 degrees or 0.43 radians, and engine or input shaft speed is 80 radian per second, and cam speed, resisting torque, and final time. And now you can see the multidynamic as a physical module that I have used a linear elastic material, and you can see the equation that is for this time dependent study, and linear static material that I have selected the specific body for linear static material, and which part are free. I mean that these gears are free, but the bar are not free. Initial values, rigid materials, gears, and etc. And then in the result section, you can see the displacement, and I'll show the unit here. It's based on centimeters, and here you can see it's between the most and the maximum is about 11.1 centimeters, the rate point, and the velocity of this gearbox There are domain numbers and sliding gears, fixed gears. There are deformation and selection. And also the angular velocity plot that you can see after 1.2 seconds, the angular velocity for each changing the gears. This is for shaft, and this is the angular velocity for gears. This is for the gears for every single from first gear to fourth gear, input and output. And you can see the angular velocity for gears, and the previous ones was for shafts. And now you can see the pin displacement. Thank you so much for watching my tutorial video until the end, and you can also download this one from my github.com/master script, and the name of this simulation is sequential gearbox with slotted cam.